Hello everyone, so I welcome you in the discrete time signal processing. Uh, Let me choose the pen first. Okay. So in this particular lecture, we will discuss about the filters. What are the digital filters? In that one, we have to see the IIR filters, IR filter and FIR filter. So in this particular lecture, we will see the both, or just we will introduce the filters first. This is all in one video. You can watch entire. So what exactly mean by filters? The filters are nothing but what you can say. It can be digital filters or analogous filters. So digital filter we can implement by using digital computers, special purpose digital hardware, and analog filters we can use the passive or active devices like resistor, inductor, and capacitor over there. That is nothing but the RLC component and operational amplifier. So filter is nothing but if you want to filter out some frequency, if you want to certain frequency, that is nothing but suppose in the entire range this is the frequency band of 20 to 20 gigahertz or megahertz. If you want to separate this frequency, that is nothing but the 20 to 2 to 20 hertz, I will say. So if you want to suppress from 2 to 20 hertz, you can use filter, either digital filter or analog filter. So you can separate that frequency also. Like this one, if you want to suppress frequency from 20 hertz and above, you can also use that same frequency. So this is the generalized working of filters. So in the active filter you can use RLC component, that is nothing but the resistor, inductor and capacitor. Also contain energy sources such as derived power from operational amplifier. Okay, means what, which are energy sources like voltage source or current source over there. And in the passive component it contains only RLC component also. Okay. In the passive component, passive filter, you will find only RLC component, that is nothing but the resistor, inductor, and capacitor component. It is not necessary that all three components are present. Okay. L is often omitted on the purpose. So, what exactly difference between active filter and passive filter? So, normally active is nothing but it is dissipating the power. Keep in mind, it is the dissipating power, that is nothing but the energy sources. We know that L and C after switch off or after transit it act as an energy source, either voltage source or current source. We know that one. And if you are using RLC component along with energy source, that is called as active filters. And if you are using RLC components only, just I am saying components only, then the filter is called as passive filter. So normally we can use either R, either L, or either C component. So this is the active and passive mode. So normally whatever the filters are there, they are categorized into four types. That is nothing but the low pass, that is nothing but the high pass, that is nothing but the band pass and band stop. So I will elaborate each and everything. So these four filters are ideal one. Okay, these are nothing but the practical one. These are the ideal filters. So how to recognize the ideal filter? That is nothing but low pass filter first of all. So low pass filter is nothing but which will pass the frequency from 0 hertz to certain hertz. 0 hertz to up to certain this frequency is there, and at this frequency this is nothing but the cutoff. After this it won't pass. So here in this one I can say that this is nothing but my pass band. This is nothing but my pass band, and this is nothing but my stop band. Stop band. So the frequency at which it will start to attenuate, start to stop the frequency, it is called as cutoff frequency, FC I will remember. Same in the high pass filter, from 0 to up to certain frequency, that certain frequency is called as cutoff frequency, FC. Up to that it will stop band, and after that the frequency are getting passes up to whatever the frequency is having. So that is nothing but the pass band over there. Pass band over there. So this is the difference between high pass and low pass. Both is having pass band and stop band. But the difference is between that in low pass filter up to cutoff frequency it will pass, and in the high pass filter from the cutoff frequency it will start to pass the frequency. In the third filter, that is nothing but the band pass filter, the name is band pass. That is nothing but band of frequencies passed by this filter. So the lower cutoff frequency denoted by FCL, that is nothing but the lower cutoff frequency, and the frequency higher cutoff frequency is denoted by FCH, that is nothing but the FC, that is higher cutoff, and H for frequency. So here this is nothing but my pass band, and this one is nothing but my stop band. This is nothing but my stop band over here. So band pass, band of frequencies passed by the filter is called as band pass filter. In the band of frequency is stopped by this filter. So in this one, it is having lower cutoff frequency, and this is nothing but a higher cutoff frequency. Higher cutoff frequency. So band stop will attenuate the frequency in between this. This will pass by this filter. This is also passed by the filter. So this is nothing but my pass band. Pass band. This is also pass band. This is nothing but my stop band. So these all filters are ideal ones. So in this lecture you will see next is nothing but what? Is nothing but my realistic, that is nothing but my practical filters. What are the practical filters? So the practical filters are it denoted by like this one. So in the ideal one it will cut off at the sharp edge. It will cut off at the sharp edge, that is nothing but the FC over there. But ideally, practically it won't. It will get some time, and after a certain time it will stop over there. Like this one, in the high pass filter, it will start to conduct from the frequency less than the cutoff frequency. Start to pass and graph like this one. In the band pass, the graph is like this one, and in the band stop, graph is like this one, as compared to ideal one. These are four as compared to ideal. So the digital signal processing is nothing but like this one. So we are having unfiltered analog signal. We are having whatever the analog signal, that is nothing but the what you can say ECG graph or EEG graph, some frequency is there. Then we are using ADC over there. So in ADC we are just sampling the signal. That is nothing but we are analog to digital converter. We are just sampling and we are converting into discrete domain over there, digitized domain. Okay. After that we are using processor. So this processor will digital filter, the whatever the unnecessary filterings are there, they will filter outward, unnecessary signals are filtered outward there, and from that again we are converting to DS, that is nothing but the digital to analog converter, and our getting the signal is like this one. That is nothing but previously just I will not this course first and I will explain it. Previously the signal is a distorted one, and after filtering we are getting the original signal like this one. So this is all happened by using filter, and previously A to D conversion, and lastly the digital to analog converter we have to use. So the ADC perform these three operations, that is nothing but the sampling, quantization, and binary coding over there. So sampling is nothing but the what we can say FS. Fs is greater than or equal to twice of Fm. This is the sampling frequency, sampling theorem. Twice Fm, that is nothing but the maximum frequency. Sampling frequency, it should be greater than or equal to twice of maximum frequency. It should be there. Uh, Next thing. So the discrete equivalent of Laplace transform is nothing but what? Discrete equivalence of Laplace transform is nothing but Z transform. Normally we are having the signal in the time domain. We are converting into the frequency domain. Frequency domain over there. So if my signal is in the analog form, I will use Laplace transform. If my signal in the discrete domain, then I have to go for the Z transform over there. So Z transform you must know. So in the Z transform we are using the two property, that is nothing but the linearity and shifting property. So how linearity will operate? That is nothing but if you are multiplying A to x of n and B with y of n, then in the output we are same multiplying the Z transform of x of n with A and taking Z transform of y of n with the B also. And the shift property, what we are doing? Shift property, if you are shifting and if you are taking Z transform in the Z domain, what will happen? It inverse will Z inverse we have to take on. Then at what time it is shifted. Then the transfer function is there. The transfer function is nothing but what? It is nothing but h of z is equal to output of z transform divided by output of input over there. That is nothing but it is nothing but the transfer function. Transfer function. So in the pole zero form, if you are taking the transfer function, here you are getting the upper side you are getting what zeros, and in the lower side you are getting the poles. Lower side you are getting the poles. So to know which system is what we can say stable, unstable, and marginally stable, we know these things. So how it is then? So this is nothing but my pole inside the unit circle. This is nothing but zero inside the unit circle, and this is nothing but unit circle. This portion is nothing but my outside of unit circle. Okay. So I have shown some stability and signal to you. From this, you can what you can say determine that the system is stable or not. Suppose the signal is like this: y of n is equal to or h of n is equal to 0.5 raised to n u of n. U of n is nothing but unit type signal, unit type discrete signal over there. If I am taking, so its z transform is like this one: 0.5 raised to n is nothing but z divided by z minus 0.5. So here you will find only 0 is not there, so 0 is at the 0, and pole is at minus 5, minus 5 not 0.5. So here the system is nothing but like this one. This is nothing but the stable system because the pole is at what right side of the unit circle. So normally we know that in any system poles and zeros are same one. Means number of poles and number of zeros are there same in quantity. The second system is nothing 0.5 is p and u of n over there. 1.5 is p n. So here if you are taking the z transform, then z divided by z minus 1.5. So here your pole is at 1.5 plus 1.5 here over here. That is nothing but the outside unit circle over there. So from this you can say that system is unstable over there. System is like this one. It is going to be increasing, and you don't know anything. And here your system is stable one. It is going to decreasing like this one. In the third system, the h of n is equal to u of n, that is the unit step signal over there. So if you are taking the z transform of this, you are getting z divided by z minus 1 over there. So the pole is at the 1 over there. So the system is called as marginally stable system. Marginally stable, you are getting all over the 1 over there. So this is all about what you can say. The system, three systems: stable system, unstable system, and marginally stable system from this one. So in the fourth case, we is there that minus 1 is p and u of n. So if I am taking z transform of this, I will get z divided by z plus 1. So the system is like this one, and you will find the waveform like this one. So this system is called as marginally stable system because it is in the left side of this one, but it is not across the unit circle over there. In the next system, n into u of n. So here you will find a repeated number of poles. Repeated number of poles. So this system is called as unstable system. The system is called as unstable system, and graph is like this one. The bounded, the output is not at bounded. It is not a bounded because it is going to be increasing at value of n over there. Okay. So if the y of n is given to you, what you have to do? You have to solve the problem for this. So 0.5 x of n plus 0.2 x of n minus 1 plus 0.1 y of n. If you want to solve this one. Okay. So just a minute. Okay, we'll solve after that. So this is not okay. Okay, so these are the frequency response. This is low pass filter, this is high pass filter, and this is nothing but band pass filter, band stop filter. So here is omega c is nothing but what my cutoff frequency. Omega c is nothing but my cutoff frequency up to pi. It is going to be increasing, up to this. So practically how it is. So this is the del of P, that is nothing but the pass band over there, 1 plus and 1 minus. Here, this is nothing but my ideal curve. This is nothing but my ideal curve over there. This is nothing but my ideal curve over there. So, some delta, that is nothing but some significance is occurring over there. So, in case of plus, we are adding this one. And in case of minus, we are adding that 1 minus delta. Then, then what will happen? This is nothing but my cutoff frequency. So what will happen up to this frequency, this is nothing but my lower pass band, that is nothing but transition band between these two del of S over there. So like this one, the stop band starts from this omega s and the pass band in between this. So in between these two is nothing but my what? That is nothing but my transition band over there. This is nothing but transition band. Okay, this is nothing but my realistic filters over there. So I think we will stop over here. In the next lecture, I will complete the remaining part of you. So thank you very much for attending this lecture. Thank you.